When dealing with a 13.8 kV feeder supplying two 2000 kV ampere transformers in a Delta-Wye configuration, protecting against phase loss, especially when a primary fuse blows, is crucial. Let's discuss the implications of a single phase outage and explore various protection methods. In the event of a primary fuse failure, the secondary voltage becomes unbalanced. This condition, known as open delta, results in the voltage on the remaining two phases increasing by a factor of approximately 1.732. This imbalance can lead to equipment overheating and potential damage. Therefore, implementing effective protection measures is essential. Several methods can be employed to protect the transformers. Firstly, consider secondary overcurrent protection. This involves utilizing the secondary circuit breaker's trip element to disconnect the affected transformer. The trip threshold should be set to detect the increased current on the remaining two phases during the open delta condition. While effective, this method can be prone to nuisance tripping if the load is already unbalanced or if a ground fault occurs on the unaffected phases. Secondly, phase loss detection can be implemented. This approach uses a dedicated phase loss relay connected to the secondary voltage. The relay is configured to trip the affected transformer specifically when it detects the absence of one phase. This method offers a more selective protection compared to overcurrent protection, reducing the likelihood of nuisance tripping. Thirdly, phase angle measurement can be utilized. A relay is employed to measure the phase angle between the three secondary voltages. During the open delta condition caused by phase loss, the phase angle shifts. The relay detects the shift and trips the affected transformer. Similar to phase loss detection, this method provides selective protection and minimizes nuisance tripping. Fourthly, negative sequence voltage protection can be implemented. A relay is used to detect the presence of negative sequence voltage on the secondary side. Negative sequence voltage arises from unbalanced conditions, including phase loss. The relay is set to trip the affected transformer when the negative sequence voltage exceeds a predefined threshold. In addition to protecting against phase loss, it's important to address the scenario of a grounded 480 volts phase. To prevent unwanted tripping in this situation, several measures can be taken. Firstly, consider using a solidly grounded neutral on the secondary side of the transformer. This provides a low impedance path for ground fault currents, facilitating their detection and clearing. Secondly, install a ground fault detector on the secondary side. This detector monitors the ground current and initiates a trip signal when a ground fault is detected, allowing for selective clearing of ground faults without tripping the transformer due to phase imbalances. When setting up these protection schemes, consider several important factors. Firstly, coordinate the protection devices. Ensure that the settings of the secondary overcurrent protection, phase loss relay, phase angle measurement relay, and negative sequence voltage relay are properly coordinated to provide selective tripping and minimize nuisance tripping. Secondly, consider the load characteristics. The settings of the protection devices should be appropriate for the load served by the transformer. For example, if the load is prone to imbalances, the settings of the overcurrent protection and negative sequence voltage relay should be adjusted accordingly. Thirdly, consider the transformer impedance. The impedance of the transformer affects the magnitude of the fault currents. The settings of the protection devices should be adjusted to account for the transformer impedance. Fourthly, regularly test and maintain the protection system. The protection devices should be tested and maintained regularly to ensure that they are functioning properly. This includes checking the settings of the relays, testing the circuit breakers, and inspecting the wiring. When selecting protection devices, consider the following factors. Firstly, the type of protection device. Choose the type of protection device that is most appropriate for the application. For example, a phase loss relay is specifically designed to detect phase loss, while an overcurrent relay is designed to detect overcurrents. Secondly, the accuracy of the protection device. Choose a protection device that is accurate and reliable. The accuracy of the protection device affects its ability to detect faults and prevent nuisance tripping. Thirdly, the speed of the protection device. Choose a protection device that is fast enough to protect the transformer from damage. The speed of the protection device is particularly important for protecting against short circuits. Fourthly, the cost of the protection device. Choose a protection device that is cost-effective. The cost of the protection device should be balanced against its performance and reliability. When implementing these protection measures, remember that proper grounding is critical for system safety and performance. Solidly grounding the neutral on the secondary side of the transformer provides a low impedance path for ground fault currents, which helps to quickly clear ground faults and prevent equipment damage. However, it's important to ensure that the grounding system is properly designed and installed to avoid circulating currents and other problems. Consider using a high-resistance grounding system instead of a solidly grounded system. High-resistance grounding limits the ground fault current to a low level, which can reduce the risk of equipment damage and improve system reliability. However, high-resistance grounding also makes it more difficult to detect ground faults, so it's important to use a sensitive ground fault relay. In addition to the protection methods discussed above, other techniques can be used to protect transformers from phase loss. One such technique is to use a voltage monitoring relay. A voltage monitoring relay monitors the voltage on the three phases of the secondary side of the transformer. If the voltage on one phase drops below a certain level, the relay trips the affected transformer. This technique can be used to detect phase loss, as well as other voltage problems, such as voltage sags and swells. Another technique is to use a current monitoring relay. A current monitoring relay monitors the current on the three phases of the secondary side of the transformer. If the current on one phase increases above a certain level, the relay trips the affected transformer. This technique can be used to detect overloads, as well as other current problems, such as short circuits. It is important to regularly inspect the transformers and associated equipment for any signs of damage or wear. This includes checking the fuses, circuit breakers, relays, and wiring. Any damaged or worn components should be replaced immediately. By implementing these protection measures, it is possible to protect transformers from phase loss and other faults, and to ensure the reliable operation of the electrical system. Remember to consult relevant industry standards and guidelines such as IEEE Standard C57.113 TM-2005 IEEE Guide for Transformer Protection for detailed information on transformer protection. Also, refer to books like Electrical Transformers by D. Parkinson and Transformer Engineering Theory, Design and Practice by H. C. Stephenson for comprehensive knowledge on transformer theory and practice. Let's delve deeper into each of these protection methods to understand their nuances and best application scenarios. Starting with secondary overcurrent protection, this method is conceptually simple but requires careful calibration. The goal is to detect the increase in current on the remaining two phases when one phase is lost. However, the challenge lies in differentiating between a genuine phase loss situation and normal load imbalances or transient conditions. To mitigate nuisance tripping, consider using inverse time overcurrent relays. These relays have a tripping time that is inversely proportional to the current. This means that they will trip faster for higher currents, which is desirable for fault conditions, but will be less sensitive to normal load fluctuations. The time current curve of the relay should be carefully selected to coordinate with other protective devices in the system. Moving on to phase loss detection, this method is more direct and reliable. Phase loss relays are specifically designed to detect the absence of voltage on one or more phases. They typically operate by monitoring the voltage on each phase and comparing it to a set threshold. If the voltage on any phase drops below the threshold for a certain period of time, the relay will trip. There are different types of phase loss relays available, each with its own advantages and disadvantages. Some relays are sensitive to voltage sags as well as complete phase loss, while others are specifically designed to ignore voltage sags. When selecting a phase loss relay, it is important to consider the specific requirements of the application. Then is phase angle measurement. This technique exploits the change in phase angle that occurs when a phase is lost. In a balanced three-phase system, the phase angles between the voltages are 120 degrees. However, when one phase is lost, the phase angles shift. This shift can be detected by a phase angle measurement relay, which can then trip the affected transformer. This method is particularly effective in systems where the load is relatively constant, as changes in load can also affect the phase angles. It is important to know that phase angle measurement relays can be more complex and expensive than other types of protection relays. Then is negative sequence voltage protection. This method is based on the principle that unbalanced conditions, such as phase loss, create negative sequence voltages and currents. Negative sequence components are components that rotate in the opposite direction to the positive sequence components. In a balanced three-phase system, the negative sequence components are zero. However, when the system is unbalanced, negative sequence components are present. A negative sequence voltage relay can detect the presence of these components and trip the affected transformer. This method is particularly effective in systems with a high degree of imbalance, such as those with single-phase loads. Also, it is important to consider the impact of a grounded 480-volt phase on the protection system. As mentioned earlier, using a solidly grounded neutral on the secondary side can help to quickly clear ground faults. However, it can also increase the risk of nuisance tripping due to circulating currents. An alternative is to use a high resistance grounding system, which limits the ground fault current to a low level. This can reduce the risk of nuisance tripping, but it also makes it more difficult to detect ground faults. Therefore, it is important to use a sensitive ground fault relay in conjunction with a high resistance grounding system. Regarding the specific requirements of the feeder circuit breaker relay, the 46, 47, and 60 functions can be used to detect imbalances in the system. The 46 function is a negative sequence overcurrent relay which can detect imbalanced currents caused by phase loss or other faults. The 47 function is a negative sequence overvoltage relay which can detect imbalanced voltages caused by phase loss or other faults. The 60 function is a voltage balance relay, which can detect imbalances in the voltage between the three phases. These functions can be used to trip the feeder circuit breaker in the event of a severe imbalance, but it is important to coordinate the settings of these functions with the settings of the transformer protection relays. A well-coordinated protection system should be able to selectively trip the affected transformer without tripping the feeder circuit breaker. Finally, let's talk about implementing a protection scheme requires careful consideration of several factors, including the system configuration, load characteristics, and available protection devices. It is important to consult with a qualified electrical engineer to design a protection system that is appropriate for the specific application. Once the protection system is installed, it is important to regularly test and maintain it to ensure that it is functioning properly. This includes checking the settings of the relays, testing the circuit breakers, and inspecting the wiring. Regular testing and maintenance can help to prevent failures and ensure the reliable operation of the electrical system.